Okay, so last week we were seeing Maschke's theorem. This is extremely important. This says, I mean, you have the usual representation, linear representation. You have a rho G invariant subspace of U, and uh, and then the claim is that there is a complementary subspace W of U, which is also rho G invariant. And I mean, the fact that there is a complementary subspace, this is standard linear algebra, but the claim of Maschke's theorem is that there is a complement, which is rho G invariant. This can also be rephrased in the other language. I mean, similarly to actions, you have two languages for representations, and the other language is CG module, where CG is the group algebra. And this tells you that if you have a CG module, which corresponds to saying that this is a representation, and you have a CG submodule, which corresponds to this rho G invariant subgroup, then there is a submodule W, such that the V is the direct sum of U and W. And of course, being a submodule for W corresponds to the fact that this is rho G invariant. More about this next. And the proof goes like this. You first choose any complement. So I mean, unless you believe to be lucky, this won't be rho G invariant. So and you take the projection from V to U along X, meaning the map that takes the sum of an element U in U and an element X in X, and send it to you. Of course, this being a direct sum, this sum is unique. There is a unique way of writing it, and any element of V as a sum of an element of U and an element of X. And so this is the kernel, this is the image. And of course, pi restricts to the identity on U. And then you do this that we have already, this operation, which we have already seen when showing that there is an inner product. Okay, well, more about this later. So it's an average. This time the average is important. When we were doing the inner product, we did not need average, but let's take this average. So this is a composition, is a map from V to V. So you first apply rho G inverse, then you apply pi, and then you apply rho G. And we had proved that if you apply psi to any element of V, you get an element of U. Okay, basically because pi sends U to U, as image U, and U is rho G invariant. Okay. Moreover, so the image is contained in U, but moreover, the image is exactly U because because psi restricts to the identity on U. And the calculation is here. I mean, this is still an element of U because U is rho G invariant. You apply pi, which is a projection on U, so you still get this same element of U. These two elements cancel. You get a sum over G of U, that's order of G times U, divide by this, and you get U. Okay. So what we have found is that psi is a linear map from V with image U, exactly U, and it's the identity restricted to U, which means it's an idempotent. Okay. And it's an important factor, though extremely elementary, that once you have an idempotent like the pi at the beginning, then this splits V as its image, which we have shown to be U, and its kernel. And I finished the lecture last Tuesday by stating that this is rho G invariant. So let's see why this is the case. Okay, this is the kernel of psi. Okay, and so remember that psi is the average over G you first take rho g inverse, then you take pi, and then you take rho g. And the important property of, psi is the claim. We will see that maps with the property that I'm going to state play a very important role in representation. Psi is rho g equivariant, which means, well, we rephrase it in terms of modules. It's similar to being linear. Well, so my claim is that if you take V, then you apply rho of something. You cannot use G because G is already taken. Let's say H, okay, and apply psi. Then you can exchange the two, okay. So I mean, for instance, if you have a linear map and this is a scalar, then of course it comes out of the map. But the claim is that this map does it for all element or rho h, for all h in G. And perhaps we'll prove this in a second, but this solves our problem because my claim was that the kernel of psi is rho g invariant. And this is the case, then kernel of psi is rho g invariant. Because if V is in the kernel, okay, and H is in H, is in G, then I want to prove that this is also in the kernel, and being in the kernel, of course, means being annihilated by psi, but by this property that I'm going to prove, you obtain this. And this is 0 because V is in the kernel. And so you obtain 0 because this being linear sends 0 to 0. So this proves that V rho H is in the kernel. So this shows that this is rho g invariant, and we've done because remember we had proved that V is the direct sum of this and the kernel. Okay, because of this property of this idempotence. But why is this so? Well, let's see. So the idea is we take a V, we apply rho H, and then you apply psi. Okay, so this is what psi is. So we obtain, we bring it inside. This is just a scalar, and rho H is linear. So you can bring it inside, and you have rho H, rho G inverse pi rho G, okay? And rho is a morphism, so you can bring it inside. And now there is a nice thing. It could have been better probably to put the inverse here, but it works nevertheless. So you have G here and G inverse here, because of course being amorphous means that this equals this. Implies, I mean, I just use it here. I brought the inverse inside. So as usual, as G ranges over G, then H, G inverse, H is a fixed element in G, ranges over all elements of G also. So let's call this X inverse, okay? So we have that X inverse is equal H, G inverse. I want to see what G is, okay? And so what I do, I multiply on the right by G, and then on the left by X, okay? So I obtain G equals XH. Let's see what this implies here. I have changed the order of summation. Sorry, I painted myself in a corner, but okay. So this is rho X inverse. Inside or outside is the same, pi a is the same, and G is XH, okay? So this is rho X, rho H. So the sum is over X this time. So you see, there is a V that is lost in the process. So, well, I could have, yes, okay, there's a V here. Okay. and see what I've done. I have just changed the name of the variable, but this is the dummy variable, variabile muta, since over which I'm summing. So this v psi rho h. So the rho h has come out. And this is exactly what this averaging does. I mean, we saw the same when we discuss inner products that are with respect to which the rho g are equivariant. Okay, so we have proved that psi is rho g equivariant, meaning this fact here. Okay, and we've seen as a consequence that the kernel is rho g invariant. Okay, and this is the trick. I mean, h comes in here, the inverse put it on the other side. You see, it enters on the left here, but the inverse puts it on the right, so it exits on the other side. Okay, this is a very nice trick, this averaging trick. Good, but since Maschke is important, let's see the second proof. So let's consider this be an inner product with respect to which the elements of rho g, or rho g is unitary. Which means, let us recall, which means that for all u, v in v, no, let's say v, w in v, and g in g, we have that v rho g, w rho g equals simply v w, okay? And you recall from linear algebra that if you have an inner product, you can bring a linear operator on the other side and you get the adjoint, okay? Which, well, we'll see this in detail, which with respect to orthonormal basis will be the transpose conjugate, but we'll discuss that again later. Since you have this equality for all v and w, and this being in products, so non-degenerate and so on, this means that rho g star has to be the identity, because there's a unique linear map that has this happen, which means that the adjoint of this is simply the inverse. Okay, so when you bring rho g on the other side, you get the rho g inverse, or better, let me write it. There are two ways of writing it, but let me write it with the inverse inside to stress that this is again an element of rho of the group G. Okay, so there is an inner product like this. So what we do, remember, we have our assumption is that U is a rho G invariant subspace of V. Okay, what we do, we consider its orthonormal subspace, whatever it's called, this, okay, which is the set of V in V, such that well, it's absolutely symmetric. Say VU equals 0 for all U in U. Okay. And since this inner product is non-degenerate, linear algebra, I've recalled these things in the preliminaries. If you need, if you want me to go through the details, I mean, I can do it. I mean, but ask me. So this implies that V is the direct sum, so far just as vector spaces, of U and its orthogonal. Okay? Orthogonal, yes, I said orthonormal. What I meant is orthogonal. And the Poynting claim, which is analogous to the claim I did on this complement obtained as the kernel of psi in the previous proof, U orthogonal is also rho G invariant. Why also? Because U was rho G invariant to begin with. And why is it so? Well, because if U is in U, or no, let's call it V is in U orthogonal, then this means that let's say V is in U orthogonal if and only if no, okay, if okay. Okay, if V is in U orthogonal, okay, consider let U in U be arbitrary and consider the product V U rho G. Okay, I want to prove that this is zero for all U in U. Okay, no, it's the opposite. Okay, so I take an arbitrary element of U, I take an element of U orthogonal, and I want to prove that this is zero, okay, for all U in U. But since the elements of rho G are unitary, this equals U rho G inverse V, okay? And this is still an element of U. By definition, every element by definition, V is an element of U orthogonal, so this being an element of U, this is zero. What I found that for all U in U, V rho G is orthogonal to U. So this means that U rho G, that V rho G is in U orthogonal. This is a geometric proof, and many people consider this to be the right proof. Yes, you have to set up an inner product with this with respect to which the rho G are unitary, but then the proof is just saying take the orthogonal of U, and this is rho G invariant, finished. Okay, so it's a conceptual proof, but you choose the one you prefer. Okay, why is this result important? Because you see, this allows you to do this. Okay, definition. There's this definition in two parts because there are two ways of speaking about representations. Let rho from G to GLV be a representation. And I won't mention it again. Of course, V is a finite dimensional vector space over C. Well, I will mention it. Finite dimensional is important. In a second, we'll see why. And G is finite. And then the rho is said to be irreducible. If the only rho G invariant subspaces are, well, as usual, the subspaces that have to be there in any case. The zero subspace, which of course invariant, and V itself, okay? So irreducible means that the only rho G invariant subspaces that you will find are the trivial ones, the trivial and the whole of this. Think of this as an analogy of simple groups, which are groups in which the only normal subgroups are the identity and the whole group. And in fact, there is a definition which is called def prime because it's the analog for CG module. So having a representation means let V be a finite dimensional, well, a CG module. I'll recall the correspondence between the two because it's important. Then V is said to be simple or irreducible if you prefer. If the only CG submodules. I could have said simply submodules because there is only one algebra, only one ring acting this CG. Submodules of V are, and you guess what, 0 and V, okay? But let me take this chance to recall once more because I used a word which was not quite appropriate the last time. Let us recall the correspondence between the two. And so how do you go from representations to modules? So rep to module. And the idea is you have rho, okay? And this is a subgroup of the endomorphism ring. This is an algebra, actually. A ring. Think of matrices, okay? N times n matrices over C. So a ring is an algebra. I mean, it's also a vector space, so an algebra. Okay? And there is this universal property of the group algebra, which tells you that here you have the group algebra, and inside here you have the group, and this yields a this yields a morphism of C algebras, or more than phi of C algebras with unit from the group algebra to NV, and having such a morphism is equivalent to say that V becomes a CG module. Because recall that an alternative way of defining a module over a ring, over an algebra, is to say that V is, in this case, a CG module if you have a morphism or algebras with unit from CG to NV. It's also a way of defining vector spaces. If you want to say what a vector space is, you take the ring of endomorphisms of an abelian group, and then you give a morphism of the algebras with unit from the field to NV. It's the same. I mean, if you read out the conditions, you get exactly the axioms of vector spaces. Okay, so this is the way you go from representations to modules. And in this correspondence, rho G invariant means being a submodule. Okay, we'll I'll write a line about this. How do you go in the other direction? This is a chance to fix a slight impropriety on my side. Well, so you have a module, okay? So which means you have this morphism phi, okay? And then you have here, so this is a morphism of algebras. You have two operations here, sum and product, and then you have scalar, multiplication by scalar. Here the same, morphisms of rings of algebras. Okay, but this is just, what's this? This is just a morphism of monoids. Because of course G has only one operation, product, so this means it preserves the product, okay? Of course, you cannot, and this is not a group with respect to multiplication. This is not a group. These are n times n matrices, so it's not, of course, it's not a group with respect to product, okay? So this is, you get a morphism of monoids here. But let's give in a number, I call it simply F, okay? But there is a very simple fact. You have a group and a morphism of monoids, which in particular, since these algebra units takes 1 to 1, okay, let's call it F. And then the image claim the image of G under F is a group. It's a very simple fact. You just need to, which is related to the fact that with a group, if you respect the operation, the product, then you respect the other operation, which means in particular the inverse. Well, you need the unit here. So why is FG a group? Because I mean, you have, of course, that if A is in G, you have, of course, that A times A inverse is 1. This is the, I mean, the fact that there is an inverse in the group. Okay, so 1 is F of 1, because this is a morphism algebra with unit. This is F times of A times A inverse. And all you know of this map is that it preserves the product. So you get this. And so this tells you that f of a, the image of an element of a group, is invertible. And its inverse is, well, I did it on one side, I should have done it on both, but of course it's the same. This is a claim that fa is invertible as its inverse is this. Okay, say fa is invertible, and you get this. And then if Fg is a group, is invertible, then Fg is a group of invertible matrices because F goes here. Think of this as a ring of matrices. And then, of course, what you obtain, that F of G, now I could have called it raw. No, let's call it raw because it's this is what it is in the end. It's my representation. It's not too difficult to fix. Then rho of G is contained in GLV. Okay, because it's a group of invertible matrices. Okay, invertible, and that's the way you have the correspondence. Last time I spoke of a morphism of groups, which in a sense is, but once you notice that the image is in GLV, the morphism of monoid is what I should have said. Okay, so far finite dimensionality has played no role, but let's now see the important consequence of Maschke's theorem, and where finite dimensionality is absolutely essential, because you have let's speak in the term in the language of representation. Let rho be a representation. If rho is irreducible, okay, stop. Okay, irreducible means that the only rho G invariant subspaces are these two. Otherwise, if it's not irreducible, then it's reducible. Then there is a subspace which properly contains 0 and is properly contained in V, U, a rho G invariant subspace. Or if you prefer, this is a CG submodule. Okay. By Maschke's theorem, V is the direct sum of U and some W, which is also rho G invariant. And this is something that you cannot do in groups. I mean, if you have a, say, a normal subgroup, which is the concept which is a rough equivalent of being rho G invariant, you don't need to have another normal subgroup that does this. S3 is typical. I mean, you have the alternating group of order 3, which is normal, but then you have 3 CEEL of 2 subgroups of order 2, which are not normal. Okay, so you split it like this, and you can keep playing the game. I mean, if U and W are reducible, you stop. Otherwise, you play again this game. With U and or. This is a case in which and or is correct, because I mean, if U and V are both irreducible, you have written V as a sum of 2 irreducible things. Otherwise, one of the two wouldn't be irreducible, and you split it, keep splitting it. You see, this is since U was different from U was different from 0. Okay, but since it's different from V, this is also different from 0. So, of course, this means that the dimension of U and the dimension of W is less than the dimension of V. Okay, the dimension of, because they have a complement which has a positive dimension, which is different from 0. This cannot go forever because V is finite dimensional. So if V has dimension n, the worst it can happen that you get to subspaces of dimension 1, okay? And so by a little more about this later. So so since V is finite dimensional, and this is important, this process will stop eventually. And you will have obtained by the end of this that V is a direct sum V1, U1, let's call K. I don't want to use N because N is usually reserved for the dimension of V, where each UI is an irreducible rho G invariant subspace. Okay, because you keep splitting it. I mean, the worst that can happen if V has dimension n, that these are of all dimension 1, I leave as an exercise if dimension of V. But this is extremely easy, then V is irreducible. The reason being simply that the only subspaces of a space of a dimension 1 are 0 and V. So they are also the only rho G invariant subspaces, okay? So the worst it can happen, they get a dimension 1, but it can stop earlier, and we'll see examples of this. Okay, so this is very important. And this is important from our point of view to study representation, because it simplifies the problem, okay? Because you see, because consider the situation in which V is the sum of this, not necessarily reducible. Rho G being linear, okay, this is just because it's a linear map, invertible then, but then you will have this, simply because being linear is respecting particular sums. But the point is, since all of these are rho invariant subspaces, UI rho G UI, and but in general, strict the domain, you don't know about the codomain, but in this case, since these are rho G invariant, this is indeed a map from UI to UI, and so it's still invertible, and so this is in GL UI, okay? It's a map from UI to UI, which keeps being invertible for the reason that we'll recall in a second. And so we have something like this. So how can we represent rho G? What we do, we do something like this. I want to represent this as a matrix. Since V is the direct sum of the UI, I can choose bases, a basis of U1, a basis of U2, and so on, and a basis of UK. And for the usual reasons, by putting together the basis of the UI, I'll get a basis of U, and I do the same here. And what we've just seen is that when I restrict rho G to UI, I get an element that maps it into UI, which means that there is something here. So if I restrict rho G to an element of U1, I get an element of U1, and this will be 0. Okay, there won't be any components outside U1 in this particular case. And if I do it with U2, I'll get something here, okay? Because rho G restricted to U2 is a map in GL U2, and this keeps going like this, and this all will all be 0, okay? Because if we apply rho G to an element of U2, you get only a component in U2 and nothing else in the other components. And so you see the situation appears to be simpler than we expected, because I mean, if the dimension of V is n, okay, then rho G is then rho G is an n by an n times n matrix, okay? So you expect that to describe rho of G, you need the square elements, okay? But what we see here, that if you choose the bases suitably, there are a lot of zeros, okay? So what we have found that okay, so let's call this rho I, okay? This is the restriction of rho G to UI. It's an element. No, okay, just a second. Okay, so consider rho I from G to GL UI, which you obtain by taking G, okay, applying rho G, and restricting to UI, okay? So rho I of G, so this is rho I of G. You restrict rho G to UI, and you get an element in GL UI. So these are these matrices here. This is rho 1 of G, this is rho 2 of G, and so on. It's just a matter of matrices. This matrix is blockwise diagonal, okay? And the blocks here called rho I, rho 1 of G, rho 2 of G, and so on, okay? And so you obtain that what is called a direct sum representation, okay? So let's say that rho is, so remember, V is the direct sum of U1 plus UK. Then you call rho the direct sum of this, okay? So rho decomposes as a direct sum representation meaning that what's this? This rho 1 rho k is the representation from V to the GLV1, the direct product of groups, GLVT to GLVK, which sends no, sorry, this is G, which takes an element G to rho 1G. So this is not exactly an equality, it's equivalent to this. Okay, so this is a way of describing what's happening here, okay? That rho G is a block matrix where each block is an element in a smaller GL, okay? Perhaps I'll finish the lecture with an example, an important example, which we can already deal with, abelian groups. This is important because what we'll see in a second is that the irreducible representations of abelian groups have all dimension 1, okay? But we'll get to there in a second. So let G be a finite, remember it's always finite, abelian group. And let rho from G to GLV be a representation. So this set rho of G, okay, which is the image of G under rho, is a set of diagonalizable, more about this in a second, commuting mutually commuting matrices. Mutually commuting is simply the fact that the group is abelian, okay? So of course, if the G commute, so that do this matrix. Why diagonalizable? Recall this is because by the consequence of Lagrange theorem, if you take any element G of G and raise it to the order of G, you get 1. So you obtain by applying rho that rho G, let's say -1 is 0, okay? I took 1 to the other side. That is, okay, that is rho G is a root of the polynomial, of this polynomial, which has distinct roots. In the complex number, the gth, order of gth roots of unity. So this means that the minimal polynomial of rho g has distinct roots. It implies that rho g can be diagonalized. Okay? And so this is a set of diagonalizable mutually commuting matrices, and I give the simple proof in the preliminaries. If you need, we can go through that. I mean, just ask. This implies that the elements of rho G can be simultaneously diagonalized. This is no diagonalized. That is, there is a basis of V with respect to which for all G in G, you have that rho G is a diagonal matrix. I'll write, okay, let me write simply something like that. Well, okay, is N actually here, okay? And I'll get back to this tomorrow, but this tells you that V is the direct sum U1, UN. So if this basis is little u, lowercase u, UN, then you take capital UI as the subspace generated by UI is the direct sum of this, where this all subspace is rho G invariant. Okay, because all matrices of this kind. So, for instance, this tells you that rho G sends U1 to the scalar multiple A1 of U1. Okay, so all these are rho G invariant. And so you see that these subspaces have all dimension 1. It's written here because they are generated by a single basis element. And then these are irreducible. Rho G invariant and dimension 1 irreducible, because dimension 1 implies irreducible and exercise that I indicated in a couple of slides ago. And this is important because it shows that for abelian groups, in principle, if you have a representation of dimension n, you should describe it with n square numbers, but you just need n. Okay, so you save space. And so I written any, an arbitrary representation as a direct sum of representation of dimension 1. And we'll resume this tomorrow morning, and we'll discuss the general case, which is in general, well, much more complicated. Okay, that's it. Thanks. See you tomorrow.